Welcome back to The Explainer. So what if I told you that you could radically transform a landscape's productivity just by changing its shape? Today, we're opening up a pretty advanced analytical toolkit for transforming landscape yield through applied geometry. We're moving way beyond your basic ecological concepts and digging into the precise math and micro-design of how shapes literally dictate yield, resilience, and efficiency in any environment.
Okay, let's dive right into this spatial puzzle. Think about the boundaries of your own site right now. The conventional wisdom for increasing yield is, well, just to buy more land, right? You expand your physical footprint. But what if the absolute secret to exponentially higher productivity isn't about the size of your space at all, but the shape of it? How exactly can we double the productive interface of a landscape without adding a single square inch to the actual property lines?
The answer lies in mastering something called the edge effect, or an ecotone. Biologically speaking, an edge is that highly productive region where two different ecosystems overlap. Think about where a forest meets a grassy field or where land meets water. This boundary isn't just a simple dividing line. It creates a third entirely distinct and way more complex system. It supports species from both adjoining ecosystems, plus it hosts entirely unique species adapted just to that transition zone. Mathematically, it's basically a zone of maximized energy exchange. And as we're going to see, shifting our mindset from viewing this as just a neat ecological theory to using it as a quantifiable design tool, well, it allows us to engineer abundance practically out of thin air.
Check out this comparison. On the left side, we've got a standard, straight-edged circular pond. Simple, right? But on the right, we have a pond with a crenellated or wavy edge. Notice how the geometry on the right actively manipulates that boundary. It actually yields 2 times the units of edge plants, like blueberries for example, compared to the simple circle on the left. The crazy part? The total water volume is exactly the same, but the earth-water interface, which is the most biologically active zone, has literally been multiplied.
Here's a quick roadmap of what we're covering today. We'll hit the math of edge geometry, strip intercropping, the aerodynamics of zigzag windbreaks, waffle iron microclimate traps, and finally, synthesizing the geometric landscape.
Let's kick things off with Section 1, the math of edge geometry and ponds.
Now, what's really interesting about this is that nature literally never builds in straight lines. It uses lobular and winding patterns to maximize surface area. It's just like how river systems wind across a landscape to increase water penetration, or honestly how the human intestine folds to absorb nutrients. Just look at the sheer efficiency of this geometric shift. If you build a pond based on an 11.3-meter circle, you create about 100 square meters of water surface. But by manipulating that boundary from a straight line to a wavy lobular edge, which we call crenellating, you geometrically double the effective circumference. You haven't taken up more total acreage, but you've doubled your productive perimeter.
And this translates directly into hard mathematical output for your plant capacity. Let's say we apply this to a regular garden bed. If you allocate a set 15-centimeter spacing for each plant, simply shifting from a straight planting arrangement to a wavy, undulating edge bumps up the number of plants you can fit from 70 to 86. That is an immediate, quantifiable boost in your yield generated entirely by ditching the straight line for a natural curve. And again, all within the exact same square footage.
Moving right along to Section 2, strip intercropping and LER.
1.67. Okay, this number is absolutely crucial. This is a land equivalent ratio, or LER, which is a metric used to evaluate how efficient it is to grow multiple crops together compared to just growing them alone in monocultures. So an LER of 1.0 is your standard baseline monoculture. An LER of 1.67? That means by integrating your planting space, you are pulling in roughly 67% more total output from the exact same physical area of land.
So the crucial point is how spatial and temporal design drive these numbers up. Like we said, a segregated monoculture is our 1.0 baseline. But if we move to strip intercropping, say integrating maize and beans, we consistently hit an LER somewhere between 1.2 and 1.5. And it gets better with staggered intercropping. One field trial analyzed successively planted maize grown with cowpea. When the maize was sown exactly 3 weeks after the cowpea, which completely mitigates the competition for light and nutrients, the system reached that massive 1.67 LER. By designing for both spatial and temporal niche differences, you're minimizing resource competition and totally maximizing your photosynthetic capture.
Zooming out to a landscape scale, alternating wavy strips of crops, like wheat alongside lucerne or corn right next to beans, create this field matrix composed of basically nothing but edges. It's a massive, highly productive mosaic. And the brilliant part is, by using parallel wavy lines, this whole complex polyculture can actually still be managed with modern, mechanized farming equipment. We are basically adapting natural edge efficiency for contemporary agriculture.
All right, Section 3, Aerodynamics of Zigzag Windbreaks.
Geometry doesn't just tell plants where to grow, it literally dictates thermodynamic capacity and wind resistance. Manipulating shapes on a macro level provides immense protective value for a site, and this brilliantly illustrates how utilizing complex geometric nets with zigzag and crescent patterns for variable winds completely alters the aerodynamic physics of a landscape. When severe, damaging winds sweep across an area, a single straight line of trees or fencing takes the full blunt force of that kinetic energy. But bowing the shapes toward the most damaging winds or creating a serrated zigzag pattern actually deflects and manages all that force.
The contrast here is honestly pretty stark. A straight fence acts as this strict, rigid barrier. It has super high wind resistance, which makes it incredibly prone to structural failure, basically getting blown completely over. A zigzag windbreak, on the other hand, utilizes aerodynamic friction. It actively diffuses and deflects the wind's kinetic energy. It stands its ground beautifully, preventing wind throw. Plus, as an awesome bonus, those little folds and embayments in the zigzag create sheltered, diverse microhabitats for plants and animals on the leeward side.
Let's move on to Section 4, Waffle Iron Microclimate Traps.
Taking things way down to the actual soil surface, let's see how ecological engineering works for really hostile arid climates. In a dry, flat environment, wind just strips the surface of any valuable resources. But if we engineer the ground to have pitted edges, kind of resembling a waffle iron, we basically build a self-sustaining ecosystem step by step. First, the wind blows over this pitted terrain. Second, the sudden geometric depression causes an aerodynamic drop, forcing the wind to drop whatever it's carrying. And third, these tiny pits actively trap that wind-blown organic debris, random seeds, and absolutely crucial moisture.
This isn't just theory, by the way. It's a proven survival mechanism. In the highly arid environment of Lanzarote, farmers use this exact pitted microdesign lined with volcanic cinder. The cold air sinks into these little pits, condensing moisture directly out of the moving air right onto the cinder layer. By simply using geometric depression, these traps pull water and nutrients straight out of the atmosphere. It allows plants, like grapevines, to thrive in places where conventional agriculture would be utterly impossible.
Which brings us to our final section, synthesizing the geometric landscape.
Whether we're curving the edge of a pond, strip planting cowpeas and maize, zigzagging a windbreak, or literally pitting the desert soil, we are applying the exact same foundational theory. Nature utilizes patterns like crenellated or lobular edges to maximize surface area and efficiency. That is the core takeaway today. Industrial landscape design relies so heavily on rigid Cartesian grids and straight lines, which minimize edge boundaries and generate massive environmental friction. But abandoning the grid for natural fractal geometries, that's not just some fun aesthetic choice. It is an absolute requirement for serious ecological engineering. It's how you double your interface, diffuse destructive energy, and stack your yields.
So I'm going to leave you with a bit of a challenge today. Take a really hard look at your own site, your own garden, or your own farm. Where are you stubbornly fighting nature with a straight line? Where could a simple curve, a zigzag, or a pitted edge unlock hidden potential and completely double your productivity? The Geometric Toolkit is right there in your hands now. It's time to start designing with the math of nature. Thanks so much for joining me for this explainer, and I will see you next time.